This is our lecture on the mole and the mole concept. We're going to be talking about Avogadro's number, talking about how we can go from grams of a substance to a mole of substance as a way of counting, all the way down to a small number of particles. By definition, molar mass is the mass of 1 mole of a substance. Now notice the units here are pretty important. Grams per mole. Now you would read that as the number of grams to equal 1 mole. Now that's important as we start to talk about this, because as we look at trying to figure out what that means, you're going to look at the grams off the periodic table, and that's always equal to 1 mole. That's how you would read that every time. So the grams are going to be unique because they're going to come from the periodic table. But that's always equal to 1 mole. It's a way of counting by mass. Maybe the best way to think about this is you go to the hardware store, and instead of counting out 1,000 bolts, they count it by weight. They count it by mass. If you go to the grocery store and you buy fruit, you don't buy it by the piece, you buy it by the mass whenever you get charged at the counter. This is how we can count atoms, because atoms are so small, we can't individually pick them out, but we can count them by mass. This formula weight in AMUs is the same number as the molar mass. Thinking about how atoms are put together, and we're looking at large quantities of those and how those work. How do we use the moles? Pretty interesting to think about in terms of moles. Notice how the mole value that we see here, the mole value is in the middle of this. They refer to this as a bridge. If you think about a bridge from the molecular scale, which is teeny tiny, like atoms, molecules, formula units, to the real world that we can deal with grams. If you notice how the mole is right here in the middle. Really important to know that the mole can get you between whatever you want to. The gram value is going to come from your periodic table. You're going to look that up, and that's going to come from your periodic table of elements. This is going to be the number of grams in 1 mole. Again, bridge over troubled waters. This is from the table. And this is the number of grams equal to 1 mole. That's the molar mass. Now on the other side of this, you've got formula units. Could be molecules could go here. That would be another individual unit. So I'll write molecules here. This could be individual atoms if we're dealing at the atomic level. But it's a small little particle that we can't count without Avogadro's number. Avogadro's number is 6.02 times 10 to the 23rd. Oftentimes you've heard the expression maybe that Avogadro's number is like a dozen. If you had a dozen cats, if you had a dozen dogs, if you had a dozen aardvarks or a dozen spoons, you would have 12 of whatever it is. If I had a mole of particles, whether it be a formula unit if it's ionic, if it's molecular, or if it's a single element, it would be composed of atoms, 1 mole would always equal 6.02 times 10 to the 23rd of those particles. Just like a dozen is always equal to 12 every time. Mole relationships. If you see this graphic, it shows you here at the top where atomic nitrogen has a formula weight of 14. Well, its molar mass is also 14.0 grams per 1 mole. If you looked at the number of nitrogen atoms, notice it's Avogadro's number, 6.02 times 10 to the 23rd nitrogen atoms. If we wanted to look at it as a molecule of nitrogen, because it's one of the Brinkelhoffs, 6.02 times 10 to the 23rd nitrogen molecules. I want you to take special notice here as we look at the number of atoms in N2. If you look at this value here, let me highlight that right there. notice that they're multiplying Avogadro's number by 2. And the reason they're doing that here for molecular nitrogen is that one molecule of nitrogen has 2 nitrogen atoms in it because it's one of those Brinkelhoffs. So it is doubled in that case in the formula. Silver ions, notice its formula weight is 107.9 AMUs. Well, that's how many grams 1 mole of it weighs. Again, Avogadro's number is not changing. Just like a dozen dogs, a dozen cats is always 12. Barium chloride, this is another really interesting example. Its formula weight, when you add it up off the periodic table, is 208.2 AMUs. It's also how many grams 1 mole of barium chloride would have to weigh. Notice on the side over here, you've got barium chloride. 1 mole of it would have 6.02 times 10 to the 23rd formula units. I'll highlight that. Now, that means that's a unit. It's ionically bonded together. So a mole of barium chloride would have that many units of BaCl2. They are sticking together. That's 1 formula unit. We could break that down into its components. Take a look at this part here. Right into this middle section. If you wanted to break it down into barium ions, it also is 6.02 times 10 to the 23rd barium ions. That's because in the formula of BaCl2, there is only 1 barium ion. So you multiply Avogadro's by 1. But if you look at what they've done to chlorine there, they've multiplied Avogadro's number by 2. Why are they doing that? Because to write a correct formula to balance the charges in the ionic formula barium chloride, there has to be 2 anions. So we have to double the number of chlorines. So it just can't be 6.02 times 10 to the 23rd chloride ions. It has to be double that because of the formula. So as you look at that, that's really confusing a lot of times for students. So when we deal with barium chloride, you doubled it for chlorine. This is a great picture of how this looks. A single molecule of water. We can't touch that. We can't see that. We can try to make that into what we can see, real world-wise. We can take a lab-sized sample of it. If we measured out a mole of water, it would have a mass of 18 grams. That is its molar mass, which is equal to its formula weight, or its molecular weight in this case. And that's always equal to the same number of particles. Avogadro's number, 6.02 times 10 to the 23rd. Again, that's molecular weight is the same as the molar mass. One's relating it at the microscopic level. One is dealing with the real world level. Notice 1 mole of carbon-12 has a mass of 12 grams. That's what Avogadro's number is based on. Here's another picture of it, thinking about with water. Water, 1 molecule is 18 AMUs. Well, I can't measure just 1 molecule of water. It's too little. But if I could collect a mole of waters, I could count it by mass of 18.0 grams. We saw that graphic earlier. This is really good too. These are all equal to 1 mole. A mole of O2 has a mass of 32.0 grams, and it's filling this balloon. Again, you'd add up 2 oxygens off the periodic table. I can't measure out 32 AMUs, but I could measure out 32 grams. 1 mole of water has a mass of 18 grams. Again, adding up the formula weight, or the molecular weight, is equal to the molar mass. 1 mole of sodium chloride has a mass of 58.45 grams. Again, that's something that's ionic. The formula weight is there. I can't measure out 58.45 little bitty formula units, but I can measure out 58.45. Just like going to the hardware store, just like going to the grocery store, we are counting by mass. Now, a couple things to think about that goes along with this. So if I had 1 mole of O2, and I had 1 mole of H2, and I had 1 mole of N2. If I counted those up, they would all be equal to 6.02 times 10 to the 23rd, Avogadro's number. But if I wanted to count them by mass, they would all be different. Just like if I wanted to look at fruit, a banana is going to weigh differently than a grapefruit is. So if I wanted to get a mole of those, the weights are going to be different, but I'm still going to get that same number. I guess maybe a better way to think about it, if I had a dozen bananas, I'm going to have 12 bananas, but they're going to have a different weight. If I had 12 apples, I'm still going to have 12 apples, but their weight would be different. These all are equal to 6.02 times 10 to the 23rd number of particles, but their masses are different because they're composed of different atoms. This is a really big concept to get a hold of. So as we think about doing these conversions, we think about trying to set these up and how these would look. Let me go back to this chart. We're always going to be given one of these things, and the mole is in the middle. Remember that the molar mass is going to be off the periodic table. The molar mass is always off the periodic table. Avogadro's number is a constant. It's like a dozen. It's a way of counting by mass. And we will use dimensional analysis to do these conversions as we're setting it up. So what we will practice doing is some of those conversions now. So if I had .0 grams of helium, and I wanted to know how many moles that was. Multiplication sign fraction. If I want to get rid of grams of helium go on the bottom. Moles of helium can go on the top. So when I do moles of helium versus grams of helium, I can relate those two things, relating the microscopic world to real world. This is where I would go to the periodic table. I'd look up the molar mass of helium. 1 mole is equal to, by the periodic table, 4.00 grams of helium. Grams cancel, leaving me with moles. If I went to my lab balance and I could measure out 4 grams of helium, I would have 1 mole. Now, if you're smarter than the average bear, and you had 8 grams of helium, that's going to be equal to 2 moles. And the reason that is, I've got double the molar mass. So if I wanted to weigh out 8 grams, I'd have equal to 2 moles. Now, if I have something like a number of particles I want to find, if I had 2 moles of oxygen, say O2 molecules, and I wanted to know how many little molecules I have stuck in there in the microscopic world, moles of O2 have to go on the bottom, and I could put molecules on the top. Well, the number of moles is 1, and we know because this is like a dozen concept that this number of molecules is the same. 6.02 times 10 to the 23rd. Moles cancel out, so I would have double Avogadro's number of little oxygen molecules. If I had 3 moles of O2, I would have 3 times 6.02 times 10 to the 23rd, because I have triple the amount of Avogadro's number. If I had 4 moles, I'd add 4 times Avogadro's number. If you go to the mole, you can always relate the difference between the two. Where it gets a little messy is if you start off with a number of grams. Say we go grams of hydrogen. Grams go on the bottom. I go to the bridge over troubled waters, which is the mole. And then I can go moles into some sort of molecular atoms. We'll just say atoms because I didn't make it molecular. So again, if I want to find this, this is off the table. So I'll go to the periodic table. 1 mole of hydrogen weighs 1 gram according to the periodic table, counting by mass. This is Avogadro's number. 1 mole is equal to 6.02 times 10 to the 23rd. So that would cancel, 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 leaving you with atoms of hydrogen. That's as complex as we'll get for tonight's homework. We'll talk about some of your questions in the lecture, and then we'll start working some of these mole problems. Thanks for listening, and we'll see how the homework goes. Thanks.